General relativity describes how mass and energy curve the geometry of spacetime with immense precision. But the Einstein field equations present a geometric identity on one side and an empirically defined source of matter on the other, leaving the microscopic mechanism, the reason matter curves spacetime, unexplained. The information manifold model, or IMM, removes space and time as foundational starting points. In this framework, physical reality and spacetime emerge as geometric residues of a more primitive structure. Every physical state begins as a configuration on a featureless, high-dimensional informational manifold, denoted as R-cubed mem. We experience this information forced through a projection operator, pi, acting as a non-invertible filter. It strips away relational phase structure, discarding mutually constrained degrees of freedom that cannot fit, leaving a lower-dimensional, observable shadow. Gravity, thermodynamic entropy, and the cosmic web emerge as mathematical artifacts of this continuous information loss. To understand how information loss builds a physical universe, we look to the quantum scale. In the IMM, observation is defined as an effective, completely positive trace-preserving map, or CPTP map. Because the projection map discards relational phase structure, the system's quantum coherence modes cannot remain stable. They undergo a mathematical process called spectral contraction. We measure coherence decay by extracting eigenvalues of the Lindblad generator. This distance to the vertical axis is the spectral gap, delta. It equals gamma minus kappa, a tug-of-war between projection density, the decoherence rate, and integration capacity, maintaining the state. Here, entropy is defined as a functional of coherence loss. Because the projection map operates continuously, monotonic entropy growth becomes a mathematical theorem derived from the contraction. The unidirectional contraction of this spectral gap defines the fundamental arrow of time. The mechanics of quantum decoherence explain entropy, but how does a microscopic loss of coherence scale up to generate macroscopic gravity? As information is discarded, the entropy production varies across coordinates, generating informational integration pressure. We measure this pressure using the global coupling invariant kappa, which compares observable data against hidden vertical fibers. High kappa means massively constrained degrees of freedom, creating inertia. Its spatial gradients generate effective metric curvature, manifesting as the downward slope of a gravitational well. By taking this pressure and varying the action with respect to the effective metric, the IMM derives its own field equation. The structure mirrors Einstein's field equations, but the tensor on the right represents the stress energy of the informational integration field, rather than physical matter. Matter curves spacetime because matter is a local concentration of kappa. In the weak field, slow motion limit, the IMM field equation recovers the Schwarzschild metric used in astrophysics. When applied to Earth's orbit, this derived metric correctly predicts the positive 38.4 microsecond per day time dilation experienced by GPS satellites, matching operational data without assuming geometric gravity is a fundamental force. Gravity is the macroscopic pressure exerted by a coherent observer state, struggling to maintain integration with a higher dimensional manifold. If gravity and quantum mechanics both stem from the spectral gap, the gap itself must change across different sizes. Under coarse graining, delta becomes a scale-dependent running parameter. This scale evolution functions as a renormalization group flow, dictating the phase boundaries where the system stabilizes into structure. This chart graphs the parameter sweep of the spectral gap. The peak of the coherence curve, marked by the vertical dashed line at negative 0.27, isolates the critical band where structural phase transitions occur. This time series plot tracks macroscopic stability. The blue mutual information proxy fluctuates before crossing the red dashed critical transition line. Past the 100 mark, interregional mutual information drops steadily as structure redistributes and clusters locally in the constructive phase. Tracking delta across these scales gives us a universal, mathematically measurable boundary between quantum coherence and stable classical structure. The final test for the IMM requires pushing it to the macroscopic extreme. If we take a three-dimensional grid, seeded with non-scale invariant noise, and apply the IMM's reaction-diffusion projection dynamics, the resulting geometry becomes a test of the model's validity. The nonlinear projection operator forces coherence clustering. The broadband noise spontaneously organizes into dense nodes and filamentary structures, carving out massive, expanding empty voids. This curvature map shows the emergent two-dimensional slice of those filamentary structures. The projection operator forces the clustering, but the resulting entropy gradients source the actual geometric curvature, locking the structures into these granular black hole anchors. On the far left panel of this dashboard, the temporal Euler curve tracks the topological phase transition. The purple line stabilizes deep in the negative axis, hitting negative 1602, the mathematical signature of a spongy, filamentary network. The IMM generates the macroscopic topology of the observable universe, the cosmic web, without assuming explicit gravitational dynamics or requiring the fine-tuned initial conditions used in standard models. In that simulation, the volume fraction of the emergent cosmic web spontaneously settles at approximately 30% structure and 70% void. This aligns with the observed matter-to-dark energy ratio in the standard lambda CDM cosmological model. But in the IMM, this ratio is a geometric necessity of the expanding entropic void. Dark energy is the informational integration floor of the vacuum. The center panel's matter-power spectrum contains a falsifiable prediction. Standard models predict power rising at microscopic scales, but the IMM's projection operator acts as a saturation cutoff, predicting the sharp downward plunge on the far right, a suppression of small-scale power. Detection of excess power at these microscopic scales by future high-resolution lensing surveys would falsify the model. However, observing this suppression would indicate the universe is a manifestation of projected information rather than space-time geometry.